Timing closure is an iterative process that helps FPGA engineers improve the performance of their designs. There are FPGA tools that can help engineers do this, but not all tools and not all FPGAs are created the same. In this interview, we will be talking to DornerWorks FPGA engineer Carl Ribbing. Carl, what can you tell me about making logic level optimizations in your FPGA design?
Timing closure is a very iterative process. You're looking for all of your critical paths that the tools can report out to you, and you're basically trying to whittle down those critical paths that are failing timing so that you can get timing closure. But we're often not going to be able to, resolve these critical paths without some kind of logic level change in your code. You can make changes with your constraints, which we'll talk to in a little bit. But generally, you're going to be looking at your critical paths, comparing it to your HDL code, making changes, rerunning, and seeing how that improves your timing performance. But it's really critical when you're looking at your critical paths that you're not just looking at the critical paths that are failing. You're also looking at the paths that are almost failing, or maybe not even close to failing, because your design is looked at as a whole. So you can kind of think of it as, I've got $100 and for timing closure, and the tool is going to use $20 for this route and $20 for this route. But that one route that it spent $20 on, it really only needed to spend $5. So if you can, reduce the number of these paths that are, even close to failing timing, and you can optimize those paths, it makes it easier for the really hard paths that you can't fix to meet timing. So you can look at your timing report, and it'll report, your start points and your end points. And often the timing, not all the tools do this. I don't think Libero does this, but I know Vivada does this. They'll give you like a percentage of logic that's routing delays, and the percentage that's logic delays. So your logic delays is the paths through the elements themselves, so through the flip-flops, the LUTs, that kind of stuff. And then the routing delay is the time it takes to get from element to element. And so if you have a path that has a very large amount of routing delay, that just means that the tools physically are placing, a flip-flop here and another flip-flop way down here, and it couldn't find, a closer place to put them. So in those kinds of cases, you can add pipelining. So, add extra registers to that path so that it can place more flip-flops along that path, so that these registers can still be placed, across the chip, but it also has these other registers that can kind of ease the routing. So pipelining will help with those kinds of cases. And then we can talk about the other side of things when, the logic delay is making up the majority of that path. And that's usually due to the fact that you may have too many levels of logic in that path. So a logic level is each combinatorial object that's in the path is a level of logic. So in your if statement, you might have some AND or gates, or you'll have some comparator logic. That is all really ends up being a logic level. And by a good rule of thumb, you really only want to have 3 or 4 logic levels in a given path, because each logic level is going to add some logic delay and routing delay. So that's going to contribute to your critical path and how fast you can run your design. So if you've got 9 levels of logic, you need to go back to your design. Maybe it's in a state machine, and you're trying to do too much in one state. So you need to break up that state machine and have that state be 2 states, and you do, part of the comparison in one state and another part of this comparison in another state. And now you've broken up your levels of logic in half. and it probably will no longer be part of the critical path. So that's the kind of stuff that you need to be looking at, taking those critical paths, comparing it to your logic, and figuring out different ways of writing things to improve performance.
How do you deal with paths around RAM and ROM in your FPGA design?
Every time, so the difference between your normal logic, which is placed in flip flops, lookup tables, that kind of stuff. That kind of logic is all throughout the FPGA. Your RAMs and your ROM blocks, those are in very specific locations. In the case of RTG4, it's a lot different than other FPGAs that I've had experience with, in that the RAM blocks are sprinkled throughout the design or throughout the FPGA, where a lot of other FPGAs, they have them in columns. So it's really easy to build. When they're in columns, it's easy to build, large arrays of RAMs because they're right next to each other. With RTG4, you're going to take a fairly large hit anytime you use a RAM or ROM. So, and even when they're in columns, you're going to take a fairly large hit going into those blocks because you're going to have some logic that's going to be fairly far away potentially. So you need to make sure you register the inputs and outputs just by default. And then another thing that I've found is really helpful is, rather than using their IP cores to instantiate the RAMs and the ROMs, and even FIFOs, it's better to write your own logic and infer those primitives, which, the way you infer them is all given to you in the libraries guide for the associated vendors. But if you infer them in your HDL code, you can apply attributes to those RAM or ROM or FIFO elements, and you can tell it what kind of technology to implement it as. So you can implement it as registers or LSRAM. And what this enables you to do is you can have experiments with your design and figure out which particular implementation of the RAM and ROM give you the best performance. Because sometimes, a register, you're okay with taking the register hit and implementing it as registers. Sometimes it's better as LSRAM. So it just gives you an easy way to experiment without having to change your code around too much.
How do you push logic into slower clock domains in FPGA design?
Often we have requirements to run our design, at a certain frequency. We might have certain throughput requirements for the data paths. But if you are finding, like, certain logic, you're having trouble meeting it at a particular frequency, it might make sense to run that block of logic at a slower clock domain. You kind of have to be careful here because you do kind of take a hit in complexity and resource and routing when moving domains, because you got to have synchronizers. You need to have buffers to transfer the data and the control logic and whatever needs to go in and out of that block of logic into the different clock domain. But you can achieve the same level of throughput at a slower frequency by just widening the data path, running it at a lower clock speed. And that might give you the additional headroom that you need to achieve timing closure.
How do you identify timing exceptions in FPGA design?
Timing exceptions is kind of like, it's a way of lessening the effort for certain paths that may not be as important, so that the tool can spend the effort on the real critical paths that really matter. So maybe you have 125 megahertz system clock, for example, and you're using that system clock to clock some logic that generates logic for an external SPI interface. And an SPI interface the external interface isn't going to be running at 125 megahertz. It's probably running at, 33 megahertz or 66 or something, some fraction of that system clock rate. So you know that there's going to be a lot of logic there that's going to be, switching every some number of clock cycles. And so if you can identify those parts of your design that you can guarantee those signals stay in that state for 2 or more clock cycles, you can put multi-cycle path constraints on those. And that essentially eases the difficulty for those paths so that the real important paths can, have priority. And you can even change your design around. Maybe there's ways for you to change some architecture of your design so that certain signals, stay constant for a large amount of time. You can put multi-cycle paths on those constraints on those paths, and now you make it a lot easier for yourself to achieve timing. For clock domain crossings, that's really critical as well. You need to make sure you constrain those properly. Otherwise, the tools are just going to try to time those crossings, and you're almost guaranteed to fail timing because the constraint it's going to assume that they're synchronous to one another, and it's going to try and time them, and you're going to have like nanoseconds to get a signal from one clock path to the other. When in reality, you only care about that path a little bit because you've got a synchronizer logic crossing those domains. So you need to make sure that you apply asynchronous path constraints on those paths that are crossing clock domains. And then the really important part is making sure to put a max delay constraint on those, because you don't want them to be false path constraints. You need to have a max delay, because if they put those blocks too far apart in your synchronizer, you'll end up having issues. But what makes that really easy dealing with cross clock domain constraints is if you design common elements for crossing clock domain, and then you can just instantiate those elements. And because you're using the same instantiated block, you can search for all paths that match that block, and you can easily create max delay constraints, asynchronous path constraints, without worrying about missing something. But those kind of cross clock domain stuff will really come out, because those are probably the paths that are the timing tools will tell you if the starting domain, clock domain, is different from the end domain. Those are often just paths that you missed with your cross clock domain constraints.